Hello, everybody. Welcome to my channel. So today I have a special guest. His name is Matt. If you probably heard of him from his channel called Physically Debunked, where he talks about all kinds of awesome sciencey stuff and arguments against God. Um, come on up, Matt. Tell us a little bit about yourself.
Well, hi there. Thank you very much for having me on your YouTube channel. It's been a while since I've been doing anything because, as I just said to you, I didn't have anywhere to live for a month, so I've been fairly inactive. But now, as hopefully you can see, I'm living somewhere. I've essentially kind of got my own studio again, so uh, hopefully I'll be producing, or not hopefully, I will be producing lots more content in the coming weeks and months. So I'll be a lot more active again from now. This is my first engagement for a while. I'm Matt. My main interests have always been in learning about the world around us, learning about how the universe works. Um, it works in such a fascinating and amazing way, and it's so interesting to learn about how exactly it does work. But also, um, I also really like all the big questions of philosophy and meaning and life and what does it all mean? Where does it all come from? What's the nature of time? What happened at the Big Bang? Is that the beginning of everything? All these kinds of big questions. And as science is our humanity's best attempt at producing knowledge and working out what's true about the world, the physics that I study is a gateway for me to then explore what I think are sensible answers and sensible possible answers to these big questions. And so, the biggest question of them all, I guess, is there a deity? Does a God exist? That's kind of the one that occupies me most on my channel, Physically Debunked. So I talk most often about why I think arguments for God's existence, why I think they fail, where I think they fail, and using current knowledge in physics and science in general to back up my arguments.
Great. So tell us a bit about your educational background, because I know you're into physics and at your university. I don't know where you go, but
Um, so I so I studied a dual honours. I studied physics and philosophy, so it was a perfect course for me at Oxford. Um, so that allowed me to explore both physics and also all these big questions. And then the crossover subject, philosophy of physics, was fascinating. Um, I studied physics and philosophy, and now I'm currently working in a cosmology department in London. Um, Specifically, I work on early universe physics. So I'm working. All my research is focused on inflation, which is a ridiculously small period of time just after uh, the Big Bang, or t equals zero in physics, I guess. Less than 10 to the minus 30 seconds after the Big Bang. Everything I study is within that really, really tiny window. Um, so that's what I'm doing at the moment. That's why I'm a PhD
Yep.
student at the moment.
Okay, great. Sounds awesome. I know in school I didn't do too well in physics. I was a science guy. I love chemistry. I have a degree in geoscience, so
Awesome.
I love geoscience, earth science, climate change. Like I'm an expert in that stuff, but when it comes to physics, not too much.
Your area is much more practical. Well,
Yeah,
everything I study is fairly irrelevant to everyday life.
yeah. All right, so one of the biggest things on people's minds is the Big Bang, right? When you talk about big ideas about the universe, everybody wants to know where do we come from? What's the first cause? What began everything, right? So I know there's many theories about regarding the Big Bang. The Big Bang's a fact. We all know it's a fact, but there are theories in science that try to explain how the Big Bang happens. And there's inflationary cosmology, there's cyclic cosmology, many different attempts to try to explain the Big Bang. Um, Now, One theory in particular, called quantum field theory, is pretty popular. It's becoming more popular, and it has a lot of explanatory power when it comes to the Big Bang. So, um, what do you think about quantum fields and how they explain the universe? And do you think they do a good job in explaining it? And tell us a little bit more about quantum fields and uh, how it ties into the beginning of the universe.
Yeah. Okay. So quantum fields are kind of, if you go through history, there's always different things that people thought made up, were kind of like the fundamental things that made up everything else. Today in physics, we almost certainly, everyone believes that we haven't actually found what exactly it is that everything is made out of, what that fundamental building block of nature is. But the deepest thing we've got to is what we call a quantum field. So the best way to explain what a quantum field is I think to picture something like a body of water on a pond, on a river, in an ocean, just a body of water. And there's lots of things that's going on in something like a fluid, in a fluid like a body of water. There's all sorts of little ripples. You can get more consistent structures such as waves which move along the surface. And a quantum field is kind of like this. So a quantum field is kind of like this body of water, this fluid, and it fills all of space, fills all of everything. It's everywhere and it's always moving, and there's all sorts of activity in it. Now, there's lots of activity which is kind of just noise. It doesn't really do anything. You can't detect all this noise experimentally. And this is the kind of thing that this is the kind of phenomenon that gives rise to what people call virtual particles. They're kind of these tiny little ripples in the fluid that don't have really any observable consequences. They kind of pop in and pop out. They have a very tiny effect. And then the things that we do see, the kind of building blocks of ordinary matter and everything we see around us, are particles. And particles are just certain structures within this body of water, these kind of consistent structures like waves. So you have two kind of things in a quantum field. The quantum field is what exists, and then you have little ripples, which are it kind of doing various bits and pieces. A quantum field can never just sit still. But then you also get these larger, consistent structures like waves through the body of water, and these are what we call particles. And so that's I guess one of the most recent kind of evolutions in physics as to what everything is kind of made out of. Before quantum fields, it was more believed that everything was made out of kind of like the tiny marble particles, and that's what made everything up. What we realize now is that these particles aren't just little marble dots, they're actually kind of structures within something more fundamental, which is what we call a quantum field. So that's what a quantum field is. It's very abstract, but mathematically it's very well defined, and you can predict all sorts of things from it and understand how all sorts of things work. So moving on now to what the Big Bang is and how quantum fields can inform our understanding of the Big Bang and the origin of the universe. Well, ultimately, what you have in the universe at any one time, according to the best physics we have at the moment, is space-time and then the quantum fields that are in it. So if you know the behavior of space-time and your quantum fields, you can predict essentially how the universe behaves, how the universe evolves through time, this kind of thing. What is the Big Bang exactly? Well, the Big Bang, it's kind of taught to people as a theory of the origin of the universe. And it's kind of, a lot of people, I think, when they learn about it in secondary school, kind of get the false impression that it's a theory of the entirety of cosmic history right up to the beginning, and it encompasses everything. It shows that there is a beginning to the universe. It's a theory of our cosmic origins. And that's kind of right in a way, but not exactly. And when you want to talk about these things philosophically, you've got to be precise. So what the Big Bang Theory really is, when we say Big Bang Theory, the Big Bang Theory is not necessarily saying that there's a beginning to the universe. What we're saying is that the universe as we see it, was not always the way it is today. The universe has changed through time. And this is different to how people used to view the universe. People used to think that the universe was basically existed in the same state for eternity. No, what we realize now is that the universe goes through different phases, different eons, different times where it's completely different. So now in the universe today, we have stars and planets and galaxies. And so you have these kind of large structures, and then they're separated from each other by massive distances. But if you rewind back 13 billion years towards the Big Bang, then you encounter something that's completely different. There's no stars, no galaxies, no planets. There's a really hot, dense, energetic various quantum fields and things like that. And if you go back to as far as we can sensibly talk about anything in modern day physics, that's the period of inflation. And so inflation, for example, how we model inflation is a quantum field right at, it's the first quantum field that we know about, essentially. And the particles that appear in it are what we call the inflaton. And what these particles do, they have a certain equation of state, and what happens is that they cause the universe during that very early time to expand extremely rapidly at a ridiculously fast accelerating rate. So using quantum field theory and a bit of general relativity, you can, and this is kind of the bottom level of my work, the kind of basics that you need to know about. You have general relativity and you have quantum field, and you have this quantum field, the inflaton, and you can work out from the mathematics of this what happens in the early universe and what we should see, what we should observe as consequences from it today. And inflation, as a theory, it's pretty good. It's pretty good. There's a lot of unknowns in it, but generally there's some decent evidence to support that it happened this way. But inflation only takes you up to a certain point. It doesn't take you right up the way to the Big Bang, or it's wrong to call it the Big Bang, really. It's more, let's call it the singularity. It doesn't take you right up to this initial t=0 singularity. But a singularity isn't a physical thing. A singularity is a point in our mathematical descriptions where quantities become infinite and the maths just kind of breaks down. So when we say there's a singularity, this doesn't mean that there really was a infinitely small, infinitely dense initial point that everything came from. What we're saying is that there's a point in the universe's past where all our current physics breaks down, and who knows what happens there. And so, as you were saying, all these kind of these other ideas for cosmology, cyclic cosmologies, eternal inflation, other multiverse theories, what these theories are looking to do is to make some guesses, make some hypotheses about what could be happening potentially around the singularity, and then what that means for reality as a whole. So yeah, quantum fields are, they don't necessarily explain where everything, or they don't necessarily explain the Big Bang singularity. But what quantum fields do is we can predict basically how the universe will evolve from an extremely early time, just based off quantum fields and general relativity.
Right. So, and these quantum fields, these are eternal things. They're the essence of reality itself, right? They make up everything.
As far as we can tell, probably with future theories, we definitely will understand them better. But at the moment, they are just this kind of almost mysterious fluid, as I said, in a way that it just exists everywhere. It exists in all space, in all time. And then particles, which are little excitations in this field, are the things that we actually observe and they pop up at different times at different places.
Which
The quantum
which could
field
be,
is, yeah, the quantum field
which
is kind of always there.
right. Oh, yeah, that was interesting what you said because I mean, you said they exist in all times and all spaces. So a universe would essentially be an emergent property of a quantum fluctuation, correct?
Um, so it depends. I mean, these are things. It's a plausible idea. So the idea you're suggesting is that if these quantum fields are in some way, if they are fundamental, you can get fluctuations as quantum fields. You can get things just kind of popping out of them. Whether they, if they're responsible for kind of the space time of the universe coming into existence, what we need to understand whether that's the case is a quantum field theory of space time, of space and time, which would be a quantum theory of gravity essentially. And that's what a lot of physicists would love to have, but we don't
Yeah.
have it yet. If in the future, when we do hopefully start develop or get further on in developing a quantum field theory of general relativity, a quantum field theory of gravity and space-time, then these questions may become much more, we can give much more sensible answers to them. It's perfectly plausible from what we know kind of now that space and time you could kind of get particles of space and time in a way, just as you get particles in a quantum field, and there may be some kind of quantum field. There may be a quantum field responsible for space-time, but at that point, things start to get a bit well-defined, and you can very clearly see the problem because quantum fields are defined over time and space. So trying to generate time and space from a quantum field is kind of tricky because quantum fields, as we currently understand them, are defined over time and space. But this is one approach to quantum gravity is to break up time and space into something more fundamental. In which case, there would then, in these theories, you would get cosmologies which explain how universes essentially emerge from these more fundamental things.
Mhm. Yeah, because I know that Sean Carroll had a talk about something called about the emergence of spacetimes, where he says that quantum fields, they get entangled, you have a break in the entanglement, then you have inflation, then you have universes and energy essentially coming out of that quantum field, and there's different whatever based on the energy of that is a geometry of space-time. So what do you think about that?
Again, it's these kind of things where we have theorists like myself and
Yeah.
Sean Carroll. We love to come up with these kind of ideas. They're really exciting, interesting to think about. They're not standard physics by any means yet, but they're plausible. They're plausible extensions of what we currently know. And what we do know is that there's got to be more to physics out there than what we currently work out. So it's nice to develop these theories and to take a look at their consequences. And hey, one of them something similar will probably end up being the case. But at the moment, we have no idea which it will be, what it will be. Is it going to be string theory? Is it going to be quantum geometry? Is it going to be causal sets? Is it going to be quantum loop gravity? We don't know. Don't know, but it could well be one of them.
Yeah, that would be amazing. If we discovered that in our lifetimes, that would be amazing. I have high hopes.
Yeah. If I have high hopes, I'm pretty young. So yeah, if we stumbled upon a quantum theory of gravity in our lifetime, it would. I mean, if you have a quantum theory of gravity, then that essentially allows you to work out what exactly is happening at a singularity at the center of a black hole or at the Big Bang. And if you understand how physics works in there, then you can make much more concrete statements about, was the Big Bang the beginning? Was there something before it? Is there something inside a black hole? What happens to things inside black holes? If we have a quantum theory of gravity, we can do all that. At the moment, It's speculation.
And that's a good segue into our next topic here, time, right? Time is something one of my favorite topics because I love to. Time is this mysterious thing, yet it's so obvious to us. It's such a real thing for us, yet it's so mysterious.
Yeah.
Now, there's a lot of theories about what time is too, right? So, um, a lot of people say though in philosophy that there's an infinite regression. If you, there must be a start. There must be a start at some point because you can't have an infinite regression of past events. I think it's nonsense, but what do you think about it? Do you think an infinite past is possible? Um, and what would a beginning mean, even? Because I think when we talk about beginning, it's very arbitrary where we set the start. Um, and time wouldn't even exist before the Big Bang. So, what do you think about the beginning, and what do you think about time?
Oh, I mean, there's all sorts of things to say about all that. It's this kind of thing is the stuff that I love talking about, and this is the kind of stuff that I spend a lot of time thinking about and reading about. This kind of stuff's great. Where to start? I think one of the things you asked me was that if I agree with these kind of that there's a problem with an infinite regression time. I similarly, like you, believe that all these kind of infinite paradoxes with infinity and infinite regresses, I don't find them very convincing arguments against, say, eternal time and things like this. I don't find them very convincing. I think infinity can often be very counterintuitive, and the mathematics of infinity can be difficult to get your head around, but the mathematics of infinity is all consistent. And so you can consistently describe and work with infinities in mathematics. And in physics, anything serious that you're dealing with is modeled with a mathematical model. And if your mathematical model is consistent, then your model of the physics is consistent. And so if mathematics with infinities is consistent, then I see no reason why infinities can't crop up physically within in physical systems. I'm on the fence. I think there is potentially some decent reasons why infinities can't end up being physical, but I also think is that there's none of the kind of paradoxes that people have proposed, I think, are genuine paradoxes. I don't think anyone's disproved that you can get infinite time and infinite quantities in the physical world. I think there aren't really any inconsistencies in there. Let's start off with eternal time, or let's go into so eternal time. So kind of the philosophical problem. A paradox that would potentially arise with infinite time in philosophy is that however many, if you split up time into individual kind of frames, and time progresses as you start at one frame, you go to the next frame, you go to another one, and so time is a sequence of these frames, and each of these frames is generated 1 second after, or one something after the other. If that's how time works, then there is a fairly legitimate concern of how you can get from these finite additions of time to an infinite amount of time. It's like with the natural numbers. However many times you add 1 to itself, you're never going to get to infinity. There's kind of this gap between the finite numbers and infinite numbers that in some ways can't be crossed. It can't be crossed by adding things up. But that's not necessarily how time works. And in fact, I think our understanding of time from general relativity is very clearly pitted against this philosophy of time. In physics, time doesn't proceed in little steps. There isn't some present that new presents keep getting added onto. That's not how time works. In general relativity, time and space, the entirety of time and space, in a sense, already exists. When you model your space-time, there's no such thing as a present. The space-time is kind of defined always. What a good way to think about this in terms of pictures is that time and space in general relativity is like modeling the universe as a big 4-dimensional shape. Okay, so instead of working in 4 dimensions, let's work in 3 because it's a bit easier. So if you have just a big kind of long rectangle, and the 2 dimensions on one of its faces are spatial dimensions, x and y, and then the dimension that runs along this rectangle is time. Well, in general relativity, space-time is like this block. It all exists. All times along it exists. All the universe along its length. It exists. Kind of, it's out there already. There's no way of defining a present for the universe. Creatures like us within the universe, because of probably because of our mental faculties and the way that our brain works, we experience time like there's a present that moves on towards the future. But this is, in my opinion, this is my opinion because of how I understand time and general relativity. This is just an illusion of some kind. When you look at the physics, there's no such thing as a present, and all of space and time is kind of already out there. And this is, this is abundantly clear in certain spaces in general relativity, where it is actually, even in principle, impossible to define a present time. And there's these kind of Gödel universes, which you can kind of imagine as like a cylinder that's kind of been knotted. In these space-times, there is no way to slice up this space-time into frames that observers will agree on. It's completely inconsistent. You can't do it. So in general relativity, you have space-times where there's no such thing as a present, even in principle. You couldn't even define one if you wanted to. And this very clearly suggests to me that the idea of a present is something that it comes from our experience of the world. It's not something that actually exists in physical reality. And so to go back to what we were saying about can time be eternal? On the picture of time and general relativity, I'd say yes, because it's not that you're producing new moments of time as time goes on. The whole space-time, the whole universe already exists out there. And I see no reason that one of its lengths can't be infinite, in the same way that the length of all the natural numbers is also infinite.
Right. So we're just looking at different slices. That's what time is. It's just different slices of the pie. It's a good way of putting it. So if there's no absolute present moment, then there's no reason to think that there's an absolute beginning moment either, right?
So this is, in some senses yes, in some senses no. And again, this depends very much on whatever the proper theory of quantum gravity is. We don't know for now. But you're right in the sense that, especially, let's ignore the Big Bang for now, because that's a very special case, that's a very special scenario, it's a very special point. We're talking about everyday life. And you say, let's say someone's being born, and you say, the person being born, they have a beginning. There's a certain point in time at which they began to exist. Well, it's a consequence of general relativity that different people, depending on how they're moving, are going to disagree over what time the baby was born. So there is no objective time at which the baby was born. It all depends on your state of motion relative to this baby. The fact that the baby exists is objective, and every observer, they will have a point in time at which they say, oh yes, the baby was born at this time. But they'll all disagree over these times, and so there's no such thing as a present in general or this basically kills the idea of present in general relativity, because you can't agree on when things happen, and it wouldn't make sense to say that. So let's go back to that baby case. The baby's born at exactly 12, according to one person. Then what that person would say is, at 12, the baby exists. But someone moving at a different state of motion relative to this baby and this clock, what is perfectly possible that they'll see is the clock actually reading, say, 12:02, and that's when they see the baby exist, when they'll see the baby born. And so then you've got these two people. One person will say, oh yes, the baby exists at 12 exactly and no earlier. And someone else is saying, no, the baby didn't exist at 12 and 12:01. The baby only exists at 12:02. And so then you have people disagreeing over whether something exists. Whether something exists has to be an objective fact. Something either exists in the universe or it doesn't. And so if you're stuck with the idea of a present, and that a present exists and that this has some objective significance, then you run into this problem where different people will disagree over what exists in that present. So this, for me, really kills the idea of that you can have that a present is something that is physically meaningful. Instead, you have these events which occur; they objectively occur, but the time that these events happens is subjective in a way. It depends on your state of motion.
Yeah, I agree with you there. All right, so now let's switch it over to the God thing. So a lot of theists will say, oh, well, God is timeless, spaceless, and immaterial. The thing that caused the universe must be outside of it, and timeless and spaceless and immaterial, because the universe has these properties. So whatever creates it can't have those properties. I think there's a lot of flaws in that idea. So what do you think about the properties of timelessness and spacelessness and immaterialness? I think they're bogus. What do you think?
So I think if you asked me a few years ago, I would have agreed with you that they're kind of bogus. Everything we know of exists in space and time. If you're not in space and time, you can't have it. It can't have any influence on us. It may as well not exist. But looking more into kind of quantum gravity theories and looking more into how we get deeper to more fundamental physics, I am much more sympathetic with quantum gravities that try and break up space and time into something more fundamental. The space-time fabric that you have in general relativity, there's all sorts of philosophical problems with it. It's a continuous shape, it's a continuous manifold, and you can ask, what does an empty, so some of the points in this space, they have things existing in them. That doesn't seem too problematic. But what about the empty points of space? Do they exist? What are they? Are they physical? And general relativity doesn't give you any answers to this. But general relativity is a classical theory. It's not a quantum theory. And so on the back of these philosophical problems, it seems to me, and to plenty of people working on quantum gravity, that space-time is something that's got to break down into something else. Space-time isn't something fundamental. It emerges from the behavior of physical things that are more fundamental. And if you're trying to build up space and time from something more fundamental, well, then it is kind of the case by definition that these fundamental building blocks are spaceless and timeless, although I don't like the words that much. But you can't presuppose space and time to build space and time. Otherwise, you haven't built it at all. You've just presupposed it. So I think that spacelessness and timelessness isn't necessarily something that's completely bogus. I think that space and time ultimately are made up of something more fundamental, but you know, the kind of way that it's applied to God as literally being kind of outside of space and time, that doesn't really make much sense, because outside is again a spatial term. It presupposes space, and
Yeah.
This is why it's almost so difficult to come up with a quantum theory of gravity, because space and time is so ingrained in the way we think, and even when when religious people are trying to talk about the properties of God as being outside of space and time, they're using the word outside, and everything you're saying is kind of presupposing space and time, and physicists have a similar difficulty. How the hell do you build up space and time out of something that's not space and time? Where does it happen? When does it happen? Difficult things, but there's good ideas out there. There's quantum loop gravity, for example, is something that goes along that track. Causal set theory is something that attempts to build space out of something more fundamental. So it's not impossible, and physics is the best way of trying to understand that. So spacelessness and timelessness aren't necessarily ill-defined, but I think what we want is a proper scientific understanding of what something like that will be, and we're coming up with some decent candidates. The kind of vague way that it's applied to God is lazy, I think.
Yeah, and how about immaterial? I mean, what would constitute a physical thing versus a non-physical thing? What do you think about that?
I mean, ultimately, there can't be a dividing line between them. Ultimately, I feel like ultimately, the only thing we care about are things that exist. If something doesn't exist, we don't care about it. It doesn't exist. And then, to me, I feel like everything that exists would be physical, because if it wasn't physical, then how on earth does it interact with the physical world? If it's completely disconnected, it may as well not exist. It can't have any influence on it. I mean, I'd almost destroy, if the theistic God did exist, I would kind of still put him under the category of physical, especially if he's going around doing miracles, because he's actually having an effect on physical things. So there's got to be some interaction. There's got to be some link between the non-God universe and God, and so God could potentially be you could put him in a certain category of physical things. He's a supernatural physical thing, but if anything interacts with the physical world, to me that's got to be physical, because you've got to be able to. There's got to be a logic and a systematic way to understand how that influence happens. So yeah, immaterial. So in the past, I think immaterial made more sense as a category. So when physicists when scientists used to think that you kind of had atoms and the void. Atoms were all your kind of material things, and the void and mental state and all these things were immaterial in a sense. They didn't have an existence in the way that the hard marbles of physical particles did. But that's kind of changed, really, especially with this picture of quantum fields and space-time, because what we kind of now realize is that particles aren't a fundamental thing. They are structures, they're ripples in this kind of quantum field. And in previous eons, people would probably have called quantum fields immaterial. But even if what we do notice most clearly are the particles within them, all these particles are things within the quantum field. And so I would call quantum fields matter in a way, or maybe not matter, but at least material. So yeah, I think immaterial is on the same kind of level as non-existence. Yeah, if something's immaterial, I don't think it exists. I think they're the
I
same
agree.
category.
I agree there. All right. So now, when it comes to the arguments for God, a lot of theists will use the contingency arguments, the ontological arguments, the cosmological arguments. There must be a beginning, therefore the beginning is God. Or I think one of the most popular ones is the contingency argument, or everything in the universe requires an explanation, but God is the necessary being that doesn't need an explanation. What do you think is a good argument that debunks that entire notion, or is better?
um, so yeah, these kind of classic arguments, ontological, cosmological, contingency, they're all kind of classic arguments, and I like to go into detail and really dive down into the detail with them on my channel, because what I think is that our understanding of physics now offers a lot of insight into the terms used in these arguments and why they're not so secure. The contingency argument is I think probably the most interesting argument there. I think it's the most of the other arguments for God. I kind of think, oh yeah, there's a term in here that I don't think you can assume that. I don't think that this means anything. I've made my peace with most of them to say that I don't think this is a sound argument at all. The contingency argument, on the other hand, I think that one of its conclusions I think is difficult to escape from, and I find myself agreeing with, and that's that there is something that exists necessarily. And that's essentially what the contingency argument, or at least a version of the contingency argument, does. What you're doing is you start off with things that need explanations because they don't exist in all possible worlds. They don't necessarily exist. There's no. It's not logically impossible to think that they don't exist. So you need an explanation for why they exist. And so, if there's all these things that you need explanations for why they exist, then there are a couple of ways you can reason from this. You can either say, perhaps all these things that need explanations kind of form this kind of causal contingent loop, and that each contingent thing within this loop kind of explains the others, and so they all, for anything you pick out, you can trace its explanation, and so everything in a way is kind of explained. But the problem with this is that how do you explain the contingent loop? Why does that particular loop of contingent things exist? And presumably there are multiple different contingent loops you can have. So that's something that I think is quite problematic. The only other get out, there are two more get outs. The other get out is also similarly unconvincing, which is to say that there's something that just has no explanation for its existence. It's just a brute fact that it exists. Yeah, it's contingent, but it exists. So whatever. This obviously isn't convincing. It's something you can argue. There's no logical inconsistency with that, but it's pretty unsatisfying, pretty unconvincing. As a scientist, I think that reality, there's a logic to it, and it makes sense, and there should be explanations for what exists and why what exists. So I don't like that explanation either. And then the only other way out of this problem is to say that there are things that exist which aren't contingent, that they have the property of necessity, that they exist necessarily, they explain their own existence. They don't need any further explanation. Now, so that essentially is the first part of the contingency argument, and I generally agree with it. I think it's a good argument. I'm fairly convinced that, yeah, there's got to be something that exists necessarily, and everything else is kind of made out of it, or the chain of logic then produces contingent things. So I think that's fairly solid. I think that there does have to exist something that exists necessarily. But then the rest of the contingency argument is then saying, well, this is what we call God, and then they try to attach properties to this, like personal qualities and love and supreme goodness and things like that. And that's when I go, yeah, this is really far-fetched. This is really qualities of greatness and moral goodness. Those don't seem like fundamental quantities to me at all. So at that point, I think that the contingency argument kind of goes off its rails. But I agree with it to the point that I think something necessary has to exist. And if we're talking about, if I'm trying to then apply that to physics, what that leads me to think is that there's something, if in a quantum gravity we broke down space and time to something more fundamental, then perhaps what we end up breaking it into exists necessarily. But more, so that's one line of thought, although it kind of feels weird that there's some particle or some quantum field that exists necessarily. It's difficult to say exactly how that works. So that's a bit sketchy. More radically, and this is what this is essentially my picture of the universe that I think, or picture of reality, which I think is most consistent and explains the most to me, is that what exists necessarily are mathematical things. It's from reading Max Tegmark that inspired me most on this. This is his mathematical universe hypothesis, that everything, that existence is the same as being a mathematical object. What exists are mathematical objects. All mathematical objects exist, and our universe is a particular mathematical object in the vast ensemble of these mathematical objects. And I feel that makes sense to me, especially with regards to the contingency argument, because mathematical truths are the kind of thing that philosophers tend to hold up as an example of necessary truths, and something that not necessarily exists, but is at least a necessary truth. If you take the mathematical universe hypothesis, you then would go further and say they necessarily exist as well. But at the very least, mathematical truths seem to be necessary truths. It doesn't seem like they can be any other way. You're forced into them, and they explain themselves. You don't go outside of mathematics to explain why a proof works. Mathematics is it explains itself. And so mathematics is basically the only thing that I can think of that feels like a candidate for a necessary entity that everything else can be built out of. In summary, I agree with the contingency argument as far as I think that something necessary exists, and then the only current candidate I can think of at the moment are mathematical entities. But that's radical, and we're so far off from actually understanding what makes up the entirety of reality that, yeah, it's speculative and yeah, it's radical, but it makes sense to me. And if I learn new things and there's a better picture of reality that makes more sense, I'll switch to that. But at the moment, that's what makes most sense to me.
Yeah, and I like how you said they try to throw all these different properties. They're just arbitrary properties. I mean, the necessary being could be literally anything at this point. We don't know, but they try to attach it as some kind of omnipotent, omniscient,
Exactly.
all-loving, unchanging, like change.
You're making this very I think whatever exists necessarily should be something simple, something very simple, like a simple fundamental building block. But no, they attach all these properties to it, and it's just like, well, how does it? None of these properties seem necessary. And so the current video that I'm editing at the moment is talking about Joshua Rasmussen's contingency arguments, and he presented it on Cameron Bertuzzi's channel. And it's the same deal. I agree with him as far as I think that something exists necessarily, but the way he argues for it is in terms of the property of maximal greatness. And I just find that, the properties, not every property makes sense. Not every property is well defined. In physics, every property that we deal with, we need a really rigorous mathematical definition for it. Electric charge, momentum, things like this. Greatness and maximal greatness just seem ridiculously vague. And if there was a way of defining greatness properly and possibly in a mathematical way, sure, I could potentially get on board with these arguments, but there just isn't, and nobody's ever proposed a really rigorous, accurate definition of what greatness would be. Until you do that, I don't think you can argue for God through the contingency argument.
Yeah, and one more point, real quick. When it comes to the arguments, a lot of the arguments are forced to basically into saying that there's an unchanging, unmoved mover, right? And I think change is a natural state of the universe. Don't you agree that change is a natural state?
This is again the kind of thing that is so difficult about quantum gravity again, is that if you want, so change seems pretty inextricably linked with time. And so if you're trying to develop physics and if you're trying to break down space and time to something more fundamental, well, does that more fundamental thing, does it have dynamics? But if it has dynamics, that implies that it's changing. But if it's changing, that kind of implies you have time. It's so difficult to get rid of these change and time. But I think that change is something that I think it falls into the same category of time, in my opinion, where it's something that we want to get rid of in a way. It's something that we want to break down, just like time, into something else. And already in general relativity, the whole universe is kind of this one big block that's already out there and already existing. And so, sure, if you're an observer within this universe, then yeah, things change for you because you have a trajectory through this universe and different quantities around you evolve as you evolve along this trajectory. But the whole block is already there. It already exists. It's already got its shape. Everything that happens within it is already there. So perhaps in a completely fundamental, if you could step out of reality, change is an illusion, and change is something that observers within reality experience. But that's potentially one side of it. The other side of it, there are quantum gravity theories which keep change as a fundamental thing. You get rid of space, but you keep time, and time is something that is fundamental. And so change is then something which is fundamental. But so perhaps it is.
Yeah. Yeah, there's I like that there's two different ways to really see it, that change is an illusion or that it's fundamental. It's actually mind-boggling. I can't get my head around it. Nobody really can. So
no, and it's unanswered at the moment. We don't know.
That's why it doesn't make sense for people to use these arguments as something that's potentially sound, because they're not sound at all. All right. Well, that was great. One last topic I want to go through. I know you have a paper coming out in regards to black holes.
Yes.
Tell us a little bit more about that, because I love black holes.
I mean, the specifics of what my paper goes into is probably not particularly interesting to a general audience, but the general motivation is interesting, as with anything in physics. The general motivation is always good. The day-to-day kind of work that I do and the technical papers I end up writing are stuff that most people wouldn't be interested in the specifics. But yeah, the general motivation. So during inflation, you have the inflaton as a quantum field. And so this quantum field fluctuates. The main quantity we're interested in is the density of this field, essentially. Some places it fluctuates and becomes very dense. Some places it fluctuates and it's not so dense. And so what we're interested in is, or what I was working on, is if there are certain regions where the inflaton gets really, really dense, there's a really massive overdensity in a certain region. If this is possible, then later on in the evolution of the universe, these regions will end up collapsing into black holes if they're dense enough. And this is what we call primordial black holes. they're black holes which are formed from the very early density perturbations during inflation. And so you've got two different classes of black holes. You have stellar black holes, which are the black holes you get formed from stars collapsing in the late universe. These are all black holes produced in the late universe. And then you have these primordial black holes, ones which are formed from the initial density perturbations in the inflaton. And so these can have some potentially unique identifiers. So there's a certain lower mass for a stellar black hole. A stellar black hole can only be, there's a minimum mass it can have. So if you see any black holes that are smaller than this mass, then you know that they're primordial ones. Why we're interested in primordial black holes is because they are a potential candidate that has recently received a lot of interest. They're a potential dark matter candidate. So dark matter is this kind of 23% or so of the universe's matter, of its mass, that we can't see, we can't detect with electromagnetic waves. The only thing we can detect from it is its gravitational influence. We know that it interacts gravitationally because it causes galaxies to spin much faster. So we know it's there, we can calculate how much of it there is, and there's actually a lovely, beautiful map that's been done of the distribution of dark matter in the sky. It forms these kind of cosmic filaments. It's really pretty. So we know it's there, and the problem is trying to work out what exactly it is. People suggest that it's some kind of particle that we don't know of yet. What I've been working on is the suggestion that it could be a load of these really tiny black holes formed in the early universe, because that kind of fits the bill. You can't see a black hole; they swallow light. They don't emit electromagnetic radiation, so you can't see them. But they're heavy, compact objects that have a gravitational influence. So whether they exist or not really sure. Jury's definitely out there, but while they do seem to be a fairly decent dark matter candidate, it's worth working on their physics and seeing what we can do with them.
Awesome. That's awesome. And I've heard that black holes in the center of them, time stops. I mean, that's something that's mind-boggling. I mean, that's obviously theoretical, but I mean, what do you have to say about that?
I mean, it's it's theoretical in the sense that nobody's ever been to a black hole and experienced time stop, but it's observational in that we've measured time dilation on the Earth. We know that it's an effect. It's predicted by general relativity, and so if you do have time dilation, then general relativity predicts you'll get masses of it near a black hole, and so the time essentially, as you get closer and closer to a black hole, people looking at you from the outside will see you get slower and slower and slower and slower until you eventually stop on the event horizon. So yeah, time, and this is again the kind of reason why there's no well-defined present in general relativity, because for one person, time's getting, or you see time for someone getting slower and slower and stopping. So you disagree over what's happening at different times, what exists at different times, and these kind of things. But yeah, time stops at the center of a black hole. That's what general relativity predicts, but that's again this kind of singularity where, yeah, the mathematics tells us that time stops essentially at the center of a black hole. Is this physical? We don't know. We'll have to wait for quantum gravity.
That's awesome, dude. Well, appreciate you being here. One thing we can agree on, though, is that the universe is mysterious, and there's so much more to learn out there. There's no reason to think that we have it all answered and figured out. But yeah, that's awesome. Appreciate you being here.
Thanks for having me on.
You're awesome, and you're welcome to come back and talk more. Okay.
I should try and get TikTok now. Or maybe I'll start appearing on TikTok.
Yeah, you do great. You'd be awesome. All right, man.
Yeah.
Thank you
very much, Mike.
Appreciate it. All right. Have a great day.
Cheers.